Hello students, welcome to the amazing platform of Physics Wala. Welcome to the PW English channel, my dear students. So today we are going to cover the lecture 8 of solid state. Okay, so my dear students, now what are we going to discuss? We have covered almost everything about the solid state. We have discussed about the various solid defects that arises. We have discussed about the various crystal systems in the solids. Now my dear students, a very small part is left, which is the magnetic properties and electrical properties that we will be covering today. Okay, it is a very theoretical part, so you need not worry about it. There will be nothing numerical related here. It will only be very theoretical, and you need not use a lot of concepts here. You only have to listen to it. It is theory. You just listen to it and you will be able to answer every question related to it. Okay, yes, perfect. So what are we going to cover today? We will be discussing about the magnetic properties first and then the electrical properties. Okay, so now what happens is, my dear students, when we talk about the electrical properties, you can see that there are some solids which can which shows magnetic properties, right? But there are some elements which do not show magnetic properties. Why is this case? Today we'll be understanding that. Okay, so basically, what are the different types of magnetic properties that may arise in a solid? Let's say magnetic properties. Okay, so what are those properties? Let's discuss about them. So the various types of magnetic properties that we will be discussing today are, first would be your diamagnetic property, then paramagnetic property, then you have, it could be ferromagnetic property, ferrimagnetic property, or antiferromagnetic property. Okay, perfect. So these are the properties which we will be discussing today. Okay, perfect. So please write it down and then we'll discuss each and every one of it individually. Perfect. Now, to understand this particular topic, you just need to have a little bit understanding about the solids. Okay, so now my dear students, when we talk about the different elements, we know how their electronic configuration is. Every element has its own electronic configuration, right? Yes, perfect. Now my dear students, what you need to understand here is a little bit about the electrons. Okay, when we talk about an electron, let's say it is a nucleus and you have an electron. Now my dear students, you have an electron and it can have two properties. It can rotate along its own axis and it will revolve around the nucleus as well. Okay, so this is the case that I can rotate around, right? Yes, and I am also revolving at the same time. Both of them are taking place at the same time. This is how an electron is moving. Okay, now the first question that arises is, why does this happen? Why your electron is rotating on its own axis, also on its axis, as well as it is revolving around the nucleus? Because my dear students, you know that when a charged particle revolves around or rotates around a whenever a charged particle rotates, it tends to lose its energy, and if it will lose its energy, it will eventually fall into the nucleus. But this doesn't happen. Why? Because it opposites that attraction by revolving around own axis. Okay, yes, so I can say that your electron can revolve, rotate, and revolve. Because of these two parts, my dear students, an electron has two different moments. It has two different moments. One is spin magnetic moment, and the other is orbital magnetic moment. Okay, yes, because of its spin along the axis and revolving around the nucleus. Okay, these are the few things that we need to understand. So the sum of these two together, give you dipole moment. Dipole moment is actually given by root L into L plus 1 plus N into N plus 2. What is this? Now let's try to understand. This is, my dear students, orbital magnetic moment. And this is your spin magnetic. Okay, and it is given by BM. BM stands for Bohr magnetone. Okay, so here L is the L is the orbit number, or you could say let's call it it actually gives you information about the subsidiary level, right? So can I say that it gives you the orbit number? Not orbit number, actually it gives you the subshell number. Okay, so it is your subshell, and your N is the number of unpaired electrons. Okay, perfect. Yes. Now, what happens is, now my dear students, when I said that your electron revolves, either it can do that in clockwise direction or it can do that in anti-clockwise direction. So, it has two possibilities. It can be clockwise or it could be anti-clockwise. Right? Perfect. And you know that in an orbital, maximum of 2 electrons can exist. Maximum of 2 electrons can exist. Out, and one will have your clockwise and one will have your anti-clockwise spin. Okay. So now what happens is, my dear students, we arbitrarily assign a value, let's say plus half to clockwise, then we'll have to assign minus half to anti-clockwise. It is not 100% that you'll always give plus half to clockwise. You can give minus half to clockwise as well. You give an arbitrary value. Okay, it is an arbitrarily given value. So now, if both of the electrons are present in an orbital, this means that total spin here would be 0 because both of them will cancel out, right? Yeah. So this is the factor which you need to understand. What happens is, my dear students, your spin magnetic moment actually dominates over the orbital angular momentum. And since it dominates over the angular momentum, what happens is, we generally calculate this as root N into N plus 2 only, because we generally ignore the L into L plus 1, that is orbital magnetic moment part. Okay, because your spin magnetic moment is dominating here. And we find out all the magnetic properties only and only based on the spin magnetic moment. Okay, yes. If you want to write all these things, please write it down, then we'll move forward. I hope you've written it. Now let's go. Read this, you'll understand a bit more. What does it say? The magnetic moment of an atom arises due to two types of motions. One is the spin of the electron around its own axis, giving rise to the spin magnetic moment, and orbital motion of electron giving rise to the orbital magnetic moment. Okay, perfect. This I told you. You can write it down. Please write it down. Next. Spin magnetic moment actually dominates over the orbital magnetic moment. Usually the orbital magnetic moment is quenched. This is the word that you see in most of the books. Quenched. This means that your spin magnetic moment is dominating over the orbital magnetic moment. Okay. Perfect. I hope you've written it. Now, my dear students, based on the spin magnetic moment, elements can be classified in different types of magnetic properties. Now, we will be discussing one by one each. The first is your diamagnetic substances. Diamagnetic substances are those substances where all the electrons are paired. There is no unpaired electron present. Okay. So, in diamagnetic substances, no unpaired electron is present. All the electrons are paired. Okay, next, the net spin magnetic moment comes out to be 0. Why? Because you know that this is equal to N into N plus 2 root, and since there is no unpaired electron, 0, so the value comes out to be 0. Okay, and you can calculate it, because you can calculate the dipole moment experimentally. For every element you calculate the dipole moment and you find out how many unpaired electrons are present, and since it comes out to be 0, then we can say that it is a It is a diamagnetic substance. Okay. Now, one more way to find out whether a substance is diamagnetic or not, what you can do is you can place it into the magnetic field. Whenever you will place it into the magnetic field, my dear students, what will happen? Your diamagnetic substance will actually repel the magnetic field. It will repel the magnetic field, and this is the thing from which you can find out whether it is a diamagnetic substance or not. Okay, so when placed in a magnetic field, diamagnetic substances are weakly repelled by the magnetic field. They are weakly repelled by the magnetic field. Perfect. Yes, please write it down, then we'll move forward. I hope you've written it. Now, the external magnetic field changes the orbital motion of the electron by a force known as Lorentz force. This force you will discuss in physics. So this line is of no use in chemistry. Just forget it. Okay. Next, this induces a orbital magnetic moment which always align itself opposite to the direction of external magnetic field. Okay. Yes. You will be discussing everything about this in the physics as well. Okay, yes. So this is your diamagnetic substances. You can pause the video, write it down, and then we'll move forward. Let's write a few examples of diamagnetic substances: benzene, diamond, N2, neon, etc. These are your diamagnetic substances. They are weakly repelled by the magnetic field. Okay, perfect. After this, my dear students, you have one more magnetic property, that is paramagnetism. So what happens in paramagnetic substances? Just let me write it down because it is just a simple part to understand. Paramagnetic substances have unpaired electrons present. So have unpaired electrons present. Okay. So they have some spin magnetic moment, and because they have spin magnetic moment, they are weakly attracted by the external magnetic field. This is the only thing that you need to remember in chemistry. Nothing else, only this will be asked. Nothing else. Okay, perfect. Please write it down, then we'll move forward. I hope you've written it now. Now, my dear students, let's talk about the third magnetic property, that is your ferromagnetism. Now, what actually happens in ferromagnetism is you have three different properties: ferro, ferri, and anti-ferromagnetism. Okay, so now what happens in ferromagnetism is, my dear students, these substances can retain magnetism in absence of external magnetic field as well. Now, when you talked about paramagnetic, I told you that they are weakly attracted in the magnetic field. Now, when they are present in the magnetic field, they behave like magnets because they are weakly attracted by the magnetic field. So they behave like a magnet. Once the magnetic field is removed, the magnetic properties will also be removed. If you want to write it down, write it here. Once external magnetic field is removed, they lose their magnetic properties. Okay, they lose their magnetic properties. I hope you're clear with this. Perfect. Please write it down. Okay. Perfect. Now, if you talk about ferromagnetic substances, my dear students, your ferromagnetic substances are actually your permanent magnets. Once you have removed the external magnetic field, still they'll behave as a magnet. They are permanent magnets. Okay, so these substances can retain magnetism in absence of external magnetic field as well. In those substances, the magnetic dipole. Now let's talk about why does this happen. So now, my dear students, what happens is, in ferromagnetic substances, initially what we were discussing about spin magnetic moment. This one single is known as spin magnetic moment, right? Yes. Now, until diamagnetic and paramagnetic substances, these spin magnetic moments were actually getting aligned either along the magnetic field or away from the magnetic field. But in case of ferromagnetic substances, many of these spin magnetic moments together with the same axis together join and form a domain, and they together form a domain. Now they have more of the power. Now just imagine what happens is, imagine you are in your locality and you started fighting with one of your friends, okay, or you are three four friends and you are actually just fighting on over small childish things, okay, that's fine. At that particular point, you all are not friends, you are now trying to fight with each other, okay. So if somebody will come, he can definitely provoke you against each other very easily, because you all are opposite to each other, right now in the locality. Now what happens, a competition arises, and now this competition is against other localities, okay. So now you want your locality to win. What will you do? You'll be friends with your locality friends, and you will create a team there. And then if anybody comes to piss you off, will you be pissed? No, you are a team now. So we can say that there is power in unity. Yes, ma'am. The same thing is happening here, my dear students. They have united together and formed a domain, formed a team, and now they are more powerful. They are even more powerful, and because they have formed domains, they have a permanent magnetic field. So in case of ferro-ferry magnetisms, my dear students, you have domains, not spin magnetic moments. Domains are formed by the joining of many of the spin magnetic moments, okay. So in those substances, the magnetic dipole of individual atoms can couple to increase the size of the magnetic domain. So what happens? They just join together and form a domain, and this is what is known as ferromagnetism. All the domains do join together. I hope you're clear with this. Please write it down. Written? Write a few examples of ferromagnetic substances. They are strongly attracted by the magnetic field: iron, copper, nickel, CrO2. This example is generally asked in exams. Okay? Yes, please write it down. Then we'll move forward. I hope you've written it. Now let's talk about antiferromagnetic substances. Now what happens in antiferromagnetic substances is, my dear students, I told you that you have domains. Let's say you have three spin magnetic moments in one particular axis. Let's say you have another domain with three magnetic moments in the opposite direction. Now, my dear students, if you see, you have a particular magnetic property here, but they both are cancelling out each other. Since the domains are cancelling out each other, then that is known as your antiferromagnetism. What was your diamagnetic substance? Where your spin magnetic moments just cancel out each other. But if your domains cancel out each other, then that is known as antiferromagnetism. This is the difference between antiferromagnetism and diamagnetic. Equal number of magnetic dipoles of the atoms are aligned in opposite direction, resulting in zero magnetic moment. Okay, so this is the major difference between the diamagnetic and antiferro. In diamagnetic, only the spin magnetic moments cancel out, but in the antiferro, your domains cancel out each other like this. So that is the way you classify it as antiferromagnetism. Okay, please write it down. Now let's talk about the last, that is your ferrimagnetic substances. So what happens in ferrimagnetic substances? Okay, magnetic dipoles, you have, let's say you have dipole moments like these, then you have some dipole moments like these, then you have, let's say, dipole moment like this. So if you see, these three cancelled out this, but this dipole moment is still left. So most of the domains cancel out each other, but still there is some magnetic property left, that is known as ferrimagnetic substances. Magnetic dipoles are aligned anti-parallel to each other, but they are not equal in number. They are not equal in number. See, these are 5 and these are 3. So they don't cancel out completely. Therefore, these substances can exhibit magnetic moment, but the magnetic moment is less than the expected value because most of them have cancelled out each other. So this is the difference between ferro, ferri and anti-ferro. Okay, perfect. Please write it down. So now you have to read this part from NCERT. I have given you a little bit of the idea. Now you have to read this part from NCERT because most of the questions that can be asked will be asked only and only from the NCERT. Nothing else will be ever asked. Okay. Yes. So you need to read the NCERT, be it for NEET, be it for JEE mains, be it for your CUET. Whatever is there in the NCERT, your questions will be made from that part only. Nothing out of syllabus. Okay. Perfect. So now, my dear students, I hope you've written till now. The next is your electrical properties. So now let's try to understand about the electrical properties. You know that on the basis of the electrical properties, you can classify your solids into majorly 3 parts. One is your conductors or insulators or semiconductors. What are conductors? Which can conduct electricity very easily. What are insulators? Who do not conduct electricity at all. What are semiconductors? Who have the tendency to conduct electricity. If you dope them, they will conduct electricity even better. If you increase the temperature, semiconductors start behaving as good conductors. Okay, so this is the way we can classify these 3. We'll be discussing these 3 in detail now. Okay, perfect. Please write it down, then we'll move forward. Now, to have a better understanding about it, we need to have a clear picture of band theory. So now what actually happens in band theory is every element has two different bands. The first band is here and the other band, let's say, is here. Okay, yeah. So now, my dear students, what actually happens is this is called as your valence band and this is known as your conduction band. So I'll not go in very detail because you only need to have a little bit of the idea. If you're good with that, everything is perfect. So now what happens is generally your valence band is completely filled. Your valence band is completely filled. Okay. And your conduction band is actually empty. So this is known as the energy gap between the 2 bands. Okay. So now what band theory says is that if in an element or if in a solid, your conduction band electrons, few of the conduction band electrons can go to the, few of the valence band electrons can go to the conduction band, they will behave as good conductors. If few of the electrons from the valence band have the capability to go into the conduction band, then it will be a good conductor. Why is this happening? Now we'll understand that. Because, my dear students, when you talk about charge carriers, which are known as charge carriers, ma'am, either they should be free electrons or they should be free ions. Right? Yes, there are no ions here. We are only and only talking about the free electrons. So the more the easily your electrons can move, the more they will conduct electricity. Yes, this means that if few of the electrons can go into the empty conduction band, they can conduct electricity because they can move around very easily. They will be more free and that is the reason they will conduct more electricity. So there are 2 things that need to be understood, that few of the electrons have the capability to go to the conduction band and the conduction band should be empty. If it is empty only, then electrons can go there and move around freely and they can conduct electricity, right? Yes. So these are the 2 things that we need to keep in mind. In metallic bonding, there is very little gap between the AMO and BMO. You need not understand what is AMO, BMO. You only need to know what is valence band and conduction band. Okay. I only want to make you understand this part. Okay. I hope you're clear with this. Perfect. Now, What band theory says, try to understand this. When we have large number of atoms, it is possible that some of the AMOs might be in the same energy level with the same of the BMOs. The energy gap almost disappears and the energy level appear to be a continuous band known as energy band. Now I'll make you understand why is this theory written. This is written for the good conductors, which are good conductors. Okay, so one by one we'll write the good conductor part. Okay, yes, so this is how I can say that this is how the energy increases. This would be your valence band, and this is your conduction band. We'll draw this, we'll use this band theory for all the three types of solids, that is conductors, insulators and semiconductors. Okay, the first one is your, now, when the electron in the conduction band can always move and contribute to the electrical conductor. Whenever an electron is present in the conduction band, if it can freely move, it can conduct electricity and it will be a good conductor. This is the first line that it says. If the valence band is completely filled, the electron can't move within the valence band and there will be no electrical conductance. If your electrons are only and only present in the valence band, they don't have a tendency to go to the conduction band, then my dear students, because valence band is completely filled with electrons, electrons do not have space to move around. They will not conduct electricity. They will not conduct electricity. But if they get some amount of energy so that they can go to the conduction band, now conduction band is empty and electrons can freely move, then they will conduct electricity. So the most important thing is you need free electrons and you need a free band, and you need a free band, right? Yes, so this is the second point. If you want to write, please write it down. If valence band is not completely occupied, electrons can move with the valence band, contributing to electrical conductance. Now, a few of you might come up with this question that, ma'am, what if the valence band has very few electrons? What if the valence band has very few electrons? Then, ma'am, the valence electrons can freely move. Yes. And then can they conduct electricity? Yes. Then they can conduct electricity. But this case arises in rare chances, so we will not discuss this part. Okay. But still, if you want to write it down, you can write this part as well. Please write it down. I hope you've written it. Now, let's talk about insulators. What are insulators? Who do not conduct electricity. Why do they don't conduct electricity, ma'am? Definitely their valence band might have been completely filled. Electrons don't have the space to move around. And ma'am, definitely electrons do not have the effective amount of energy to reach the conduction band. And since they cannot go to the conduction band, they cannot conduct electricity. Right? Yes, these are the few things that might have happened before in insulators. Yes, now let's try to read it. Okay, there is a large gap between the conduction band and the valence band. Valence band is completely filled, hence can't be promoted from valence band to conduction band. Electrical conductivity is negligible. I hope you got the idea. So what does it say? It says that in insulators, what happens is you have two bands and the gap is a lot, This is your valence band and this is your conduction band. Electrons are filled in the valence band completely. So your valence band is completely filled. So do the electrons have empty space to move around? No, they do not have the empty space to move around. Can they overcome this energy gap? They do not have enough energy to go to the conduction band. Now, since electrons cannot go into the conduction band, since they do not have empty space to move around, they cannot conduct electricity. Right? Yes. So, please draw it down first. I can say very high. Okay. Now, write it down. And then this. There is a large gap between conduction band and valence band. Valence band is completely filled. Hence, electrons can't be promoted from a valence band to the conduction band. Electrical conductivity is negligible. Okay, perfect. Now, let's talk about the conductor. If we talk about a conductor, my dear students, let's say you have a valence band here, and let's say you have a conduction band here. So what happens in conductors is, this is your valence band and this is your conduction band. Your valence band is completely filled with electrons. Your valence band is completely filled with electrons. So what happens is your electrons can definitely go into the conduction band because both are overlapping. Since both are overlapping, definitely a few of the electrons can go to the conduction band, and if they go to the conduction band, they have an empty space, and since they have an empty space, they can conduct electricity, and that is the reason they are classified as good conductors. Okay, perfect. Till now everything is clear, everything is easy, understood every part of it. Now I am telling you one thing, my dear students. What if I increase the temperature of a conductor? If I increase the temperature of a conductor, what actually happens is, first you will tell me, if I increase the temperature, what will happen? Will conductivity of the conductor increase, or will the conductivity of the conductor decrease? Just think about it and tell me. Try to think about it. Try to think about all the logical answers, that if we increase the temperature, what will happen? Will the conductivity of conductor increase or decrease? Try to think about it. Okay. If you try to think about it, you will say that, ma'am, obviously with increase in temperature and always conductivity actually increases. So in conductors also conductivity should increase, right? Yeah. If you're thinking so, let me tell you, you're absolutely wrong. Why? Why are you wrong? Because, my dear students, now you have to think of the logical reason here. Actually, when you increase the temperature, conductivity decreases, okay, and not increases. What actually happens is, you know that in a conductor, your both the bands do overlap. Both the bands do overlaps. This is your valence band and this is your conduction band, and there is very little energy difference. They actually, both of them overlap. Okay, you know that most of the electrons are present in the valence band. That is, your valence band is completely filled. Okay, ma'am, perfect. If you increase the temperature, my dear students, what will happen? You will increase the temperature, more and more of the electrons will go to the conduction band. And with the increase in temperature, what will happen? Your electrons will start moving into the conduction band. And there will be a time where whole of your conduction band will be completely filled. Now, since your whole of the conduction band is completely filled, is there any empty space for the electrons to move? Because you need free electrons, you need free space for conduction, but you don't have empty space in the conduction band now. And eventually your conductivity decreases, So in the case of conductors, when you increase the temperature, the conductivity actually decreases. I hope you're clear with this point. Please write it down and then we'll move forward. You draw these diagrams. Whatever I have said till now will be written in the slides. You can write it down. I hope you're clear till now. Now just see. In conductors, the valence band is completely filled, but it overlaps with the conduction band. Therefore, energy required to promote the electron from valence band to conduction band is nearly zero. Yes. High electrical conductance is observed due to the movement of electrons in the conduction band. Your electrons can move in the conduction band and eventually they are very good conductors. Okay, perfect. They can conduct electricity. I hope you have written till now. Now just see. Next point. Yeah. As the temperature is increased, the conductivity of the metal decreases. Why does it decrease? I gave you the reason. A high temperature, the nuclei start vibrating, causing obstruction to the movement of electrons. Either you can give this technical answer, or you can say that when you increase, the conduction bands get completely populated, leaving little space of movement of electrons. So there are two different reasons. You can use any reason. I generally give this reason because this makes you understand things very easily. Okay? Yes, perfect. Please write it down, then we'll move forward. Now, the last is your semiconductor. So now, let me talk about semiconductor. So what happens in the case of a semiconductor is this is your valence band and this is your conduction band. Okay. Valence band where your electrons are present, and this is your conduction band, and this is your delta E, that is the difference in energy. Okay. So in case of semiconductors, actually what happens is, yes, there is an energy gap between the valence band and conduction band, but the energy gap is not very large. Okay. If you increase the temperature, a few of the electrons can go to the conduction band. If a few of the electrons can go to the conduction band, obviously the band is empty and there are free electrons which can move around, so they can conduct electricity. So semiconductors do behave as do conduct electricity at high temperatures. Why? Because we have increased their conductivity, right? Yes. So semiconductors can show, or we can say semiconductors conductivity can be increased either by increasing the temperature or by doping. I'll also make you understand what is doping, but till now I hope you have you have a little bit of the idea about the band theory of a semiconductor. So please draw it. I hope you've drawn it. Now, let's read a few points about semiconductors. In some conductors, conduction band and the valence band are very close to each other. They are close to each other. Electron can be promoted from valence band to the conduction band by supplying heat, by increasing its temperature. When the electrons are promoted, they also create a positive hole in the valence band, because when electron will go, then there will be a hole. Electron was negatively charged and now there is a positive charge, or there is zero charge. We can say it is positively charged now. There is an absence of electrons, so that is what is known as hole. The electricity through the movement of electrons create N-type semiconductor. Now I'll make you understand what is N-type semiconductor and what is P-type semiconductor, but you just need to have an idea that semiconductors do conduct electricity when we apply heat or when we dope them. Okay, perfect. Please write it down. I hope you've written it. Now, electrical conductance through positive holes create P-type semiconductor. We'll be discussing both of the type of semiconductors right now. When temperature is increased, the extent of solid defect is increased and the electrical conductivity of the semiconductor increases. Because if you will increase the temperature, obviously more of the valence band electrons can go to the conduction band and eventually they can conduct electricity. Above type we have discussed is intrinsic semiconductors. These are the intrinsic semiconductors. When you dope them, they are your extrinsic semiconductors. Okay. Yes. Intrinsic semiconductors at 0 Kelvin conductivity will be 0. If you are not providing any heat, their conductivity will be 0. If you provide them heat, then they'll conduct electricity. Okay. Perfect. Please write it down. I hope you've written it. Now, let's talk about extrinsic semiconductors. Now, how do extrinsic semiconductors arise, my dear students? Extrinsic semiconductors are the conductors in which you dope them, and you make them good conductors. How do we increase their conductivity? So basically, your semiconductors are from group 14. Generally, your semiconductors are from group 14. If you will see the periodic table, whenever you have studied inorganic, you definitely have come across the group 14 elements behave as semiconductors. Okay. How do they behave as semiconductors and how can we increase their conductivity? We can increase their conductivity by giving some impurity or by adding some impurity, or we call it doping. Okay. What is doping? That is, we add some impurity or we add some element from group 13 or group 14, and based on which element we have added, it can be a N-type semiconductor or it can be a P-type semiconductor. Okay. So now for understanding this, you need to have a little bit understanding. Let's take a common example of a semiconductor from group 14. Let's say you have silicon. Okay. So now, my dear students, group 14 elements have 4 valence electrons. So they can make 4 bonds together. So silicon makes bonds like this. And this is how. Okay. This is how this is how your semiconductor looks like, and it is not conducting electricity right now. So what happens is, we can increase its conductivity by adding some impurity to it or by doping it. What impurity are we adding, or with what are we doping it? We are doping it with either addition of group 14 element, group 13 element, or group 15 element. Okay, now let's try to understand. This is the basic idea of a semiconductor. Okay, so the first case is, we are doping group 14 element, that is one example I have given you, with group 15 element. So let's try and understand this. You had this semiconductor. Okay, now what happened is, it is saying that you are doping it, we are doping it, and we are doping it with a group 15 element. Let's say we are doping it with arsenic. Okay, so now what I did is, I removed one silicon and I added a arsenic to it, As. Okay, now since it belongs to group 15, you know that group 14 elements have 4 valence electron and group 15 elements have 5 valence electrons. So group 15 elements have 5 valence electrons. It has 5 valence electrons. Now see, you know every bond is made up of 2 electrons. So 1 electron will be of arsenic and 1 electron will be of your silicon. Again, 1 electron will be of arsenic, 1 for silicon, 1 for arsenic, 1 for silicon, 1 for arsenic, 1 for silicon. Ma'am, 4 of the valence electrons of arsenic have been used. Still, 1 electron is left. Yes, and my dear students, that 1 electron is present here. And this is actually your free electron. This is your free electron because it is not involved in any bonding. Since it is not involved in bonding, it is a free electron, and you know that free electron is a charge carrier. It is a charge carrier. And since it is a charge carrier, it will conduct electricity. And since this is being done because of a free electron that is negatively charged, we call such type of conductor as N-type semiconductor. Okay, so whenever we dope with a higher valency element or group 15 element, an extra electron is left, and because of the movement of that free electron, electricity is conducted, and we call it a N-type semiconductor. I hope you're clear with this. Please write it down. Perfect. Now let's try and understand the second case, which is, now we are doping the group 14 element with a group 13 element. Okay, so again I have the silicon, that is my semiconductor. I know that they have 4 valence electrons, and all the 4 valence electrons are used in forming the bond. Yes, now what happens is, now I dope it with the group 13 element. Okay, so now group 13 element, I'll add here group 13 element. Let's say, which element should we use? Let's use aluminium. Let's use aluminium. Now, if I talk about group 13 element, my dear students, they have 3 valence electrons. They only have 3 valence electrons. They only have 3 valence electrons. I know that one bond is formed by 2 electrons. Okay. So ma'am, let's say this bond is formed. Let's say this bond is formed with 1 electron of aluminium and 1 of silicon, 1 of aluminium and 1 of silicon, 1 of aluminium and 1 of silicon. But here, my dear students, let me use pink color. Here, no electron is present. No electron is present. And this is known as, and this part is known as hole. This is a positive hole. This is a hole because electron is not present here. Now, since electron is not present here, what happens is, my dear students, one of the electron which they both were sharing, this electron tries to occupy this space. Now, when this tries to occupy this space, a hole is created here. Similarly, now this electron will try to take this position, one hole will be here. So, this is how one electron keeps, each electron keeps on rotating. And that is what it looks like, that first the hole was here, then it came out here, then it came out here, then here, then here. Randomly, your hole keeps on moving. But can I say that your electron was actually trying to move? Yes, ma'am. Electron is moving because the hole is moving. So it seems like it is conducting electricity because of the movement of a hole, right? Absence of electron. But it is conducting electricity, that we can see. So this type of semiconductor is known as p-type semiconductor. P-type semiconductor, where your conductivity is due to the movement of the hole. Where your conductivity is due to the movement of the hole. This type of conductor is known as your p-type semiconductor. Whenever the doping is of a group 14 element with a group 13 element, then that type of semiconductor is known as a p-type semiconductor. I hope you're clear with this. Perfect, my dear students. Please write it down. With this, we have ended our session. You have a homework here, my dear students. You have to read the NCERT of this particular part. You have to read NCERT of both the particular parts. In fact, you will have to read NCERT of defects, solid defects, magnetic properties, and you have solid defects, you have magnetic properties, and what we did, yes, we did electrical properties as well. Okay, these all three topics you have to read NCERT, because the questions will be asked only and only from NCERT, because nothing higher level can ever be asked, because it is a theoretical part. Okay, yes, perfect. With this, we have ended our solid state chapter. I hope you have understood each and every part of solid state. We took a complete 8 lectures to complete this, my dear students. So I hope you are crystal clear with each and every topic. I enjoyed teaching this part very much. We'll cover the next lecture. We'll cover the next chapter, which is surface chemistry, in the coming lectures. So I hope all of you are super excited, super happy, and you have gained a lot from this particular chapter. So keep studying, keep enjoying. Thank you so much. Bye-bye. Take care.